Hi everyone. Today we're going to be learning about vectors and their applications, and I'm sure these sound familiar from physics, but today we're going to learn more about them in terms of mathematics. So let's get started. The first thing we're going to focus on is the vocabulary to understand, and I wrote them first, so if you want, you can copy them, pause the video, and copy them down. So let's read them. Okay, so for scalars. Scalars involves magnitude and can be represented by real numbers. A vector is a directed line segment which models a quantity's direction and magnitude, which you know from physics. And vector quantities, so vectors basically represent magnitude and direction. Initial and terminal point. So for a vector symbolized by the points OP, and vectors are usually going to be symbolized with a boldface type. So let's say that your vector is OP. The first letter is the initial point, and the last letter is the terminal point. And this is useful in knowing the direction of the vector. So let's say you have a vector for here. The initial point, we said it was OP, so the initial point, the first letter is O, the second letter is P. So it goes this way, right? You know that the arrow is going that way, in that direction. And so knowing these points gives the direction of this vector, and PO would be the opposite of OP. Next is the resultant vector, which is, like we've learned, the sum of two vectors, A plus B, and opposite vectors. Okay, so for every vector V, there is a vector negative V that has the same magnitude but opposite direction. And this kind of ties on to the initial and terminal point. Like I said, if there was a vector pointing in the direction of OP, so again, like I said, OP, OP, it would go like this way, and with the same exact magnitude, PO, P would start over here, and O. See the same magnitude, but they're in different directions, so these are opposite vectors. And when you add opposite vectors, you get 0, which would be the 0 vector. So that's just another component of vectors. Okay. And next is the position vector. So a vector U with its initial point at the origin in a rectangular coordinate system and its endpoint at A, comma B is A, comma B. So U equals A, comma B. So this basically means in a coordinate system, starting at the origin with a vector over here, and the vector ends at A, comma B. This is basically the position vector. So a position vector is expressed in coordinate pairs. So vector U, let's say like we name this U, vector U, you can identify it with its terminal coordinate, AB, because it started at the origin. Okay? And you can do many things with that, which we'll get to later. And horizontal and vertical components. So these are the components which make up a position vector. So in the case that I just described over here, A and B, so A would be the horizontal vector, the horizontal component of the vector, and B would be the vertical component. And like we learned in physics, every vector has both horizontal and vertical components from, to make like the actual vector, on both ends. It's being, influenced by the horizontal and vertical sides. Next term is the direction angle, and the direction angle is the positive angle between the x-axis and the positive vector. So again, with this case over here, this position vector, this would be the direction angle, the angle between the actual position vector and the x-axis. Okay, and so how to find the magnitude and direction angle of a vector. So the magnitude or length of vector u equals a comma b is given by absolute value of u equals the square root of a squared plus b squared. And the direction angle, theta, satisfies tan theta equals b over a, where a cannot equal 0. So a cannot equal 0. So let's do this example. Find the magnitude and direction of u equals -3, 4. So what we're going to do over here is we're going to use the equation above, u equals the square root of a squared plus b squared. So let's go ahead and do that. So u equals square root of, so a comma b, so let's make -3 equals a and 4 equal to b. So -3 squared plus 4 squared. And this equals the square root of -3 squared, the negative cancels out, so it's 9, plus 4 squared, which is 16. Now this gives me the square root of 25, which is an easy answer, and it equals 5. So that's the magnitude of this vector. Magnitude equals 5. And now to find the direction angle of u equals -3, 4. And remember, direction angle, you have to use degree mode in your calculator. So what we're going to use is this equation, tan theta equals b over a. So we did that over here. And remember, to find theta, you have to take the inverse tan of -3 over 4. And plugging that into my calculator under degree mode, you get theta equals -36.87 degrees. All right. Now, next topic. How exactly do we find the horizontal and vertical components? All right. So for a vector u with magnitude, absolute value of u, and direction angle theta, a equals the absolute value of u cosine theta, and b equals the absolute value of u sine theta. So basically this is saying, this gives us the directions on how to find the horizontal and vertical components of a vector when we're not given them. Okay? So you can say that u equals a comma b really is the absolute value of cosine theta comma absolute value of u sine theta. So let's do an example. So vector w has a magnitude of 65 and a direction of 31.6 degrees. Find the horizontal and vertical components. Okay, so when we want to find vertical and horizontal components, we're focusing on magnitude. So for this equation, for this problem, direction we can kind of ignore. So let's go ahead and do this problem. All right. So what we're going to do is we're going to use the equations from above. So to find the horizontal component A, and I'm going to shorten component, you need the absolute value of u cosine theta. Okay? So vector w has a magnitude of 65. So that's going to be 65 for u, and a direction of 31.6. So cosine theta equals 31.6. So we do use the direction angle. And that's how you're going to find the horizontal component for this vector. So we'll hold on to that one, and now we're going to do the vertical component, B. So let's do this. Vertical component, B. For this one, you need absolute value of u sine of theta. Okay? So this one is going to be u, again, we named this one in the example, we named this vector w, but again, it means the same thing. So vector w was 65 and sine 31.6 degrees. So make sure that you're following degree mode. So let's plug these into our calculators. Okay. 65 cosine 31.6 gives us a horizontal component of 55.4. I'm going to round up. Okay. And for the vertical component, I'm going to do the same thing except replace cosine with sine. And hold on. Okay, 65 sine 31.6. And that gives me, for my vertical component, B equals 34.1. So those are our horizontal and vertical components for vector W with a magnitude of 65 and direction of 31.6 degrees. All right. So let's go on to the next page. This other example tells us or asks us to write each vector in figure 31 in the form A, comma B. So it gives us an image, and what it wants us to do, again, is look at the image and write each vector in the form AB. So let's go ahead and do that. Okay. So let's look at vector U first. So I'm outlining that over here, vector U. And over here, I'm outlining it in red, and I'm going to also outline its direction vector, direction angle in red. So this would be 60 degrees. Okay. And we know that to write it in the form of A comma B, we need the horizontal magnitude and direction angle. Okay. So the magnitude for U is 5, as given in the image, and A comma B is the horizontal and vertical components. So what we're going to do is just substitute AB for the horizontal and vertical components. And in the equation that we used previously, again, the horizontal to find the horizontal component, you'd have to use the absolute value of the magnitude, cosine theta. And for the vertical component, you'd use the absolute value of the magnitude, sine theta. So this is the magnitude, absolute value. And for the horizontal component, we're going to use cosine. So this is 5 cosine, and we know that the direction angle is 60 degrees. So 5 cosine, 60, which is A. That's A. And then for B, you will get 5 sine 60. And you can simplify that. The cosine of 60 and sine 60, we know what that is. Cosine of 60 is 1/2, and the sine of 60 is the square root of 3/2. So 5 times 1/2 is 5/2. And then the sine of 60 is square root of 3/2. So 5 times square root of 3/2 is the vertical component. So that's the first one. And then for v, let's do it in a different color. V is this one. Okay, so v is 2. V has a magnitude of 2, so v is in green. Okay, so magnitude of 2 cosine, and then the direction angle for v is 180. And then same thing for vertical component, but we just use sine. Then this gives you, because we already know that the cosine of 180 is -1, and the sine of 180 is 0, so 2 times -1 is -2, then 2 times 0 is 0. That's how it can be simplified. And then for w, we'll use the blue. And w has a magnitude of 6, and that's already positive, so absolute value is going to stay 6. And then the direction angle is 280. Okay, so horizontal component, A, is 6 cosine 280. And then the vertical component would be 6 sine 280. And this one isn't as easy as v or u, because we don't necessarily know what cosine of 280 or sine 280 is off the top of our heads. So we'd have to use the calculator for this one. And again, in degree mode. And we'd get 1.04 for the horizontal component and -5.91 for the vertical component. Okay? And then over here it just gives you a list of vector operations. So when you have two vectors that you're trying to add, a, b, and c, d, you add their horizontal components and their vertical components. And when you are trying to multiply a vector by k, you basically use the distributive property where you multiply a and b separately, both by k. And then if a equals a1 comma a2, then negative a equals negative a1 comma negative a2. And you remember how we were talking about opposite vectors? You know, it's it would still equal a. It would be the same magnitude, but in a different direction. So they'd have the same value, but they'd just be negative. And then the last operation is when we're subtracting two vectors. Again, we take them individually by their horizontal and vertical components. So AB minus CD would basically mean A minus C, comma B minus D. All right, so let's do an example. So let vector u equal -1 comma 3 and v equal 2 comma 2. So for the first one, we're going to find u plus v. So let's do that right now. So u, like we said, was -1 comma 3, and then v was 2 comma 2. Now what we're going to do is take both of their horizontal and vertical components and add them. So -1 plus 2, comma, which would give me the horizontal component, and then 3 plus 2, which would give me the vertical one. So you add them, -1 plus 2 equals 1, and then 3 plus 2 equals 5. So this would be the answer. How about -2u? Okay, so u equals -1 comma 3, and one of our vector operations was when we're multiplying a vector by a number, we use the distributive property. So -2 times -1 comma 3 would basically mean -2 times -1. That would be the horizontal component, and then -2 times -3. that would be the vertical component. Okay, so -2 times -1 would be 2, and then -2 times 3 is just -6. Okay, and then last one, 3u minus 2v. Okay, so u equals -1, 3, and then v is 2, 2. What we're going to do is, this includes both. So not only are we multiplying, we're subtracting as well. So for u, we're going to multiply it by 3. 3 times -1, 3 minus 2 times 2, 2. And so 3 times -1, 3, when you multiply 3 by both the horizontal and vertical component of this individual vector, 3 times -1 is -3, and then 3 times 3 is 9. So this would equal -3, 9. And then we're subtracting this by 2 times 2, which is 4, and then also 2 times 2, which is 4. So we're going to subtract -3, 9 minus 4, 4. And again, with subtraction, it's the same thing as addition. We are taking them by their horizontal and vertical components. So -3 minus 4, 9 minus 4. So -3 minus 4 is -7, and 9 minus 4 equals 5. Right? So this is the answer. Okay, and unit vector. So a unit vector is another term that we're going to define, and I'm going to do it on a separate sheet. Don't have that much room. So unit vector. A unit vector is basically a vector that has magnitude of 1. Okay, and so we use the following variables I'm going to write to represent the magnitude of 1 for the vector. So I would equal 1, 0, and then j would equal 0, 1. So basically, I would be the horizontal component because it's 1, 0, and then j would be the vertical component because it's 0, 1. And so the unit vector is applied when we see the IJ form for vectors, and the IJ form for vectors is basically just another way to write vectors. So let's say for a given vector, if v equals a, b, then v also equals ai plus bj. And again, where did we get the I and j's from? We got them from the unit vectors, and we said that I was 1 for the horizontal component and j was 1 for the vertical component. So again, when I is next to a, it's just multiplied by 1. So it doesn't make a difference. It's just a different form to write vectors when you place the I in the horizontal component and the j in the vertical component. So that is basically that for the IJ form. Alright, so now we're moving on to dot products. And what exactly is the dot product? So let's define it. So the dot product of the two vectors u equals a, b, and v equals c, d is denoted u dot v and is read u dot v, and it's given by this equation over here. So u dot v equals ac plus bd. So basically, for the dot product, in order to find it, we're multiplying the horizontal components and vertical components separately, and then we're adding them together. So let's look at this example. So find the dot product. All right, so we're taking the horizontal components first. So 3 times 2, I'm going to that equals 6, so I'm going to write it there. And then we're adding it to the vertical component product. So, and then 2 times negative 4, that equals negative 8. So 6 plus negative 8 is the dot product. And we know that 6 plus negative 8 equals negative 2. Okay? And then for this one over here, it's giving us the two vectors in ij form. And we know that this just means the same thing as any other vector, just worded differently. So, okay, this would equal 4, 5, and this is negative 1, comma 3. So, again, we're multiplying the horizontal and vertical components. So, 4 times negative 1 is negative 4, plus 5 times 3, which is 15. And negative 4 plus 15 gives us a dot product of 11. And orthogonal vectors, these are basically vectors that when we take the dot product of them, the dot product equals 0. So I'm just going to put, so when dot product equals 0. So hypothetically, let's say these two vectors, 3 comma 2 and 2 comma negative 4, equal, like once we did this and we got 0, we would have labeled it as an orthogonal vector. So there are many properties of the dot product shown over here. So the first one, u dot v equals v dot u. They're interchangeable. And then b is basically the distributive property. So when you're taking this dot w, w is going into the u and the v separately. And then for c, anything multiplied by 0 equals 0. For d, this is again is the distributive property, so it's u this time, dot in parentheses v plus w. You see over here it equals that u dot v plus u dot w separately. And for e, when it's ku in parentheses dot v, the k is it can be taken out and multiplied by u dot v, or u can be taken out and multiplied by kv. Yeah, they're very interchangeable, and that helps a lot in some problems. And f over here, u dot u would equal u squared. So the geometric interpretation of the dot product. So if theta is the angle between the two non-zero vectors u and v, where 0 degrees, where theta falls into either between 0 and 180 degrees, then u dot v equals the absolute value of u times the absolute value of v cosine theta. Or equivalently over here, cosine theta equals u dot v over the absolute value of u times the absolute value of v. So let's do this example over here. So find the angle between the two vectors u equals 2 comma 3 and v equals 1 comma 2. All right, so let's do that. And right now we know that we're trying to find the angle, so we're going to use this equation. So over here, as you can see, cosine theta equals u dot v over the absolute value of u times the absolute value of v. And when we plug in the numbers, u equals 2 comma 3 and v equals 1 comma 2, this is what we basically are getting. So 2 comma 3 dot 1 comma 2, and then we'll plug in the numbers on the bottom as well. And the dot product on top equals to 7 once we work that out. And you may be wondering why over here the coordinates on the bottom are being squared in this next step over here. Well, given that these terms are in absolute values, we have to square them and then take the square root of them later on in order to cancel out any potential negatives. So once we work out the bottom as well, we get the square root of 65. So when you plug it into your calculator, 7 over the square root of 65 equals to approximately 0.87. And again, in the equation that we used, we were trying to find the cosine of theta. And we have to take the inverse cosine to find theta. So inverse cosine of 0.87 equals roughly 29.5 degrees. So that would be that for this example. The last main idea that we're going to be talking about involves the law of cosines and the law of sines. So hopefully you guys remember those. If you don't, that's fine. That's what the notes are for. So yeah, let's fill this out. So law of cosines equals c squared, equals a squared plus b squared minus 2ab cosine of big C. Okay? And the law of sines equals, it's a ratio if you remember, so a over sine of a equals b over the sine of b, which equals c over the sine of c. So you're probably thinking what this has to do with vectors, and in a lot of story problems you'll be like given some information and you'll have to find some angles or magnitudes, and they'll come in handy, these laws. So let's go ahead and try one story problem, and these can be found in the book. So I'm only going to do one given that, and the rest you can again refer to the book for, given that, I don't want this video to take forever. You guys are probably, okay. Anyway, so this is, we'll try number one. So we will be doing the first example. So a ship leaves port on a bearing of 28 degrees and travels 8.2 miles. The ship then turns due east and travels 4.3 miles. How far is the ship from port? What is its bearing from port? Okay, so that's a lot of information that we can use. So I'm going to do this example over here for more room. All right, so let's go ahead and start drawing this scenario out. And again, we're doing this one. All right, so the ship is leaving port at an angle of 28 degrees and it travels 8.2 miles. So I can draw a vector and say that this is 8.2 miles. Okay, and it's at a 28 degree rate, so compared to a vertical line over here, this would be, that would be 28 degrees, right? And then you can connect it from over here. So that's, looks like, a triangle. Okay, and then it turns east for 4.3 miles. So again, we can draw another vector turning east, 4.3. And then to connect these, we can draw a resultant vector, which again is the sum of both of them, both of these vectors, which we will be finding. All right, so what this problem is asking, so we're supposed to find the, like how far the ship is from the port and what is its bearing from port. Okay, so let's start off by just labeling all of these lines, so we can understand them a little bit more. So this could be P, and then we'll make this corner over here A, and E over here, and yeah, and we can make this N. All right, so we know that this is 28 degrees, and again, I told you that this was a vertical line. So this over here, PAN, makes a it makes a right triangle. So we know that this over here equals 90 degrees. And so if this equals 90 degrees and this is 28 degrees, then we can find angle A by adding these two and then subtracting that by 180. And with that, we get 62 degrees. All right? So we know that this angle over here is 62 degrees. And why is that important? Well, now that we know that this angle is 62 degrees, this over here is a horizontal angle, is a horizontal line, I'm sorry, and that has an angle of 180, as we know. And that makes this angle over here, and then this angle over here, supplementary angles. So when we subtract 62 from 180, we get this angle over here, which turns out to be 118 degrees. All right, so now that we have figured a lot of information about this diagram, we can now use the law of cosines to find the magnitude of PE. And this magnitude would basically be tell us how far the ship is from the port. Okay, so let's go ahead and do that. So PE, absolute value of squared, equals 8.2 squared plus 4.3 squared. Sorry, over here. And then you subtract it, 2 times 8.2 times 4.3. Then cosine of 118. All right? And then when you plug this into the calculator, you get that PE squared is approximately 118.84. Then to find PE, square root both sides. So you get PE equals 10.9, which is approximately 11 miles. So we answered the first part of the question. 10.9. And then what is its bearing from port? So that's the second part of the question. And with this, and for this part, we will use the law of sines. So to find the bearing of the ship from port, we have to first find this angle over here, APE. So we need to find this. And in order to find it, we can use the law of sines. So because we already know a proportion of sine 108 sine of 118 degrees over 10.9. So sine of APE over 4.3 equals the sine of 118 over 10.9. And again, when you solve for this, then plug this into the calculator, you find that you find that APE equals 20 degrees. So APE equals 20 degrees, and plus the 28, the original 28 that was the angle from the port at first, that equals 48. So that's the bearing of the port. So the total is 48. So how far is the ship from port? It's about 11 miles. And what is its bearing from port? Approximately 48 degrees. And yeah, so these are basically vectors and their applications. Thank you everyone for watching, and now if you're feeling comfortable enough, you can go ahead and take a look at the homework problems. Thank you.